All right, guys, the next step in our study of covalent bonds is to take a look at electronegativity and how it makes molecules either polar, okay, which are going to stick together, or nonpolar, that are not going to stick together, okay? And so this is just the next little step in our sequence of covalent bonding. So we know that covalent bonds are going to share electrons, right? And we can represent covalent bonding using Lewis dot structures. And that's what we've been doing the last couple weeks. Last couple classes, we've took the next step of Lewis dot structures and used them to figure out the shape of the molecules, right? Whether it was tetrahedral, if it had 4 bonded pairs, or pyramidal, if it had 1 lone pair with 3 bonded pairs. Because remember, we used the Vesper theory, the valence shell electron pair repulsion, all right, to say that those electron pairs, those 2 dots on all sides of the center atom, are going to want to be as far apart from each other as possible. So they're going to push away from each other, and they're going to make specific shapes. Now, what we're going to do is the next step is we're going to take a look at the electronegativity differences between the atoms that make up a molecule. And as the notes that you have already seen talked about, if these electrons are being shared fairly, that means the electronegativity difference is very low. All right, and so it's going to be nonpolar. But if the electronegativity difference is very high, that means that the electrons are not being shared fairly, and we're going to make a polar bond and a polar molecule. So let's see how this works. Right here in front of you in this activity, the top part is an electronegativity chart. So it's a periodic table, and instead of all the other basic facts a periodic table gives you, like the atomic weight and number of protons and whatnot, this is going to give you the electronegativity value. Now remember, electronegativity is the attraction for electrons, right? So if something has high electronegativity, it's going to have a high value, a high attraction for electrons. So we can see on our on this chart here that the highest electronegativity values are these guys over here, and the 2s, 3s, and fluorine, that makes 4. And the lowest electronegativity value is down here, okay, with cesium and francium. They're 0.7 and 0.8. All right, so we can see there's a drastic change or difference in electronegativity. For the most part, metals on this side have low electronegativity, and nonmetals over here have high electronegativity. Okay, and so that, remember, is the attraction for electrons. So nonmetals are going to be very attracted to electrons. They're going to want to steal other electrons away because they're so attracted to electrons. But metals, on the other hand, are not attracted to electrons, and they just want to give them up. That's why nonmetals gain electrons, become negatively charged, and metals lose their electrons to become positively charged in an ionic bond. Now, that's all fine and dandy when we're talking about metals hooking up with nonmetals, but remember, in covalent bonds, 2 nonmetals are hooking up. So they're not going to be able to, like we discussed this earlier, they're not going to be able to rip electrons away from each other, okay, because they're both going to be, pulling with a lot of strength. So what we're going to see is that if the pulling is equal, okay, one's pulling in equal and opposite directions, we're going to call that what's called a non-polar bond, all right, meaning that the electrons are being shared fairly. However, if one is pulling slightly harder than the other, but not totally ripping that electron away, we're going to see that that's called a polar bond. Okay, so nonpolar means equal sharing. Equal share of electrons, versus polar is unequal sharing. And the way we determine this is we take a look at our scale for electronegativity, and we take the difference. Okay, we take the difference between the two. We subtract. All right, so for example, if we have a like NO2, nitrogen dioxide, right, and it's made up of nitrogen and oxygen. So if we take the difference between the two, 3.5 minus 3.0, we get a difference of 0.05, right? And that value is going to determine whether it is polar or nonpolar. Okay, so let's take a look at some examples. So we need to keep in mind that if the electronegativity difference is 0 to 0.49, that is a non-polar bond. Okay, meaning that those electrons are being shared fairly. If we have an electronegativity difference between 0.5 and 2.1, that is a polar bond. Okay, they're still shared, but it's not fairly. And then last but not least, if we have it greater than 2.1, it is an ionic bond. Okay, we're not sharing anymore. That strength of one just overpowers the other and rips it away. Okay, so these two guys here, the first two, are still covalent. The last one is ionic. So covalent still means that they share electrons. All right, so you guys need to keep that in mind when you are answering the questions for part 1. Okay, all of these are found in your notes. If you didn't take the notes, then you didn't do your homework. All right, and first off, and then secondly, perhaps please find somebody who did, okay, so that they can help you out, and maybe they'll be nice enough to give you the notes. But please make sure that you get the notes before you start this. All right, so in part 1, you're going to be using that electronegativity chart that you see on the top of your papers and your notes to answer these questions. Okay, it's gonna go over, what's the trend for electronegativity, doing the differences and figuring out if it's something is a polar bond versus a non-polar bond versus an ionic bond. Okay, taking a look at comparing two atoms, seeing which one's more electronegative, and then in starting at numbers 8 and beyond, here's going to be actually hooking up and making different compounds. So please make sure when you have to do an ionic bond, okay, like we see here, this one, number 8, ionic bonds, make sure you always crisscross the charges. All right, because ionic means that the nonmetal has so much strength that it's ripping that electron away from the metal. And so the nonmetal is going to be negative, the metal is going to be positive. So you must crisscross the charges. So once you've identified two elements as having a difference of over 2.1 in electronegativity value, you need to look up their charges on the periodic table and crisscross the charges to make legit neutral compounds. Okay, so please keep in mind for that one. On the other hand, you're going to be also using electronegativity values to put together covalent compounds. Okay, so number 10, for example, says use the electronegativity table above to create 3 legit neutral examples of compounds with polar covalent bonds. Okay, covalent means that you must use Lewis dot structures. All right, so to make sure that you have enough hydrogens in your molecule or enough oxygens or whatever, you must draw out the Lewis dot structures to figure out what the molecular formula will be. Remember, you cannot have any lonely electrons, so make sure that when you do your Lewis dot structures, you're hooking up, the correct number of atoms with each other. Okay, so part 1 is just working with electronegativity. Okay, figuring out the differences, subtracting differences between two atoms, and seeing if something is nonpolar covalent polar covalent, or straight up ionic. All right. So in part 2, we're going to put it together with everything that we have done from this point, from this point back for covalent molecules. So we're going to do Lewis dot structures, we're going to do structural formulas, we're going to predict the shape, we're going to do the bond angle, we're going to figure out if this molecule overall is a polar molecule. The way we can do that, okay, polar member means it has charges. Okay, so one side is going to be slightly positive and one side is going to be slightly negative. All right, the way we do that is we take a look at the electronegativity differences. So what I'm going to do up here on screen is about 2 of them together with you, maybe 3, we'll see. And so please follow along as I do this. So let's just go through, let's walk through the first one, carbon tetrachloride. All right, if we take a look at our periodic table, we're going to see that, remember, carbon has 4 valence electrons, chlorine has 7, and if we have 7 chlorines, 7 times 4 is 28, plus the 4 from carbon, that is a total of 32 valence electrons. So when we do our Lewis dot structure, we're going to have 32 dots. Oh my goodness. So let's do that real quick. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so at this point, that should be easy for you. If it's not, you need to spend time doing this. Okay. Now the structural formula, remember, is the same as the dots. You're just exchanging 2 dots for a line. So the structural formula for CCl4 would look at carbon in the middle with a line to each chlorine on all 4 sides. Okay. Now looking at our Lewis dot structure, we can see that the carbon is the center atom, which means we take a look at the center atom and we see that the carbon has 4 sides with electrons. That's 4 electron domains. All of them are paired to a chlorine. So if they've got 4 electron domains, all bonded pairs, 0 lone pairs, that is a tetrahedral shape. Bond angle is 109.5. You just have to memorize it, okay? So the more you do, the easier the bond angles will come. Okay, now to figure out if this molecule is going to be polar, okay, and be able to dissolve in water and stick together to become a liquid, we have to look at the difference in electronegativities. So if we look at the chart, okay, on the top of your paper, the difference in electronegativity between chlorine and carbon is 0.5. Okay, so we looked at chlorine, I believe that's 3. Carbon is 2.5. So 3 minus 2.5 is 0.5, right? Now, according to our scale, 0.5 means it is a polar bond. It means that the chlorine is pulling harder on the electron than the carbon. Okay, and the way that we represent that is with arrows. So we draw an arrow to the more electronegative atom. So what we'll do is in the next one over, we're going to redraw our structural formula. And we're going to put arrows, okay, towards all the chlorines because they're going to pull harder than the carbons. Okay, and now we can see we have to look at the which way the arrows are pulling and if they're pulling in equal and opposite directions. So these are chlorines all around, so they all have equal strength. We have one pulling up, we have one pulling down, that cancels each other out. We have one pulling left, we have one pulling right. Those also cancel each other out. Okay, so if all arrows cancel each other out, that means we have a non-polar molecule. If you remember from the notes, non-polar means it will not dissolve in water because water is a polar molecule. And we cannot smell it. Okay, so those two are no's. All right, so you must be patient. You must go through all of these steps, all right? And you must put it all together in order to be able to do this. All right, so let's do 2 more together to see how this is going to work. All right, so the next one we're going to do together is SiO2, okay, silicon dioxide. So if we look at our periodic table, silicon is in the same group as carbon, so he has 4 valence electrons. Oxygen, each oxygen has 6 valence electrons, so 2 oxygens is 12. That means 12 plus 4 is 16. So total number of valence electrons in a molecule is 16. So what that means is that we should have 16 dots in the Lewis dot structure. So let's do that. Si, 1, 2, 3, 4. Oxygen, 1, 2, 3, 4, 5, 6. Here's our other oxygen, 1, 2, 3, 4, 5, 6. Shoot, we have lonely electrons. We have 4. 1 on each oxygen and 2 for this silicon. So what does that mean? That's right, we're going to double them up. We're going to put them together to make double bonds. So let's do that. We're going to do silicon. We're going to move these guys in the middle. We're going to put our oxygens on the side. Okay, so it's going to look like this. All right, our Lewis dot structure. Now our structural formula, remember, is the same as our dots. It's just lines instead of dots. So we've got Si in the middle, and we've got 2 lines on either side to make the oxygens. And remember, we can use our honk 1, 2, 3, 4 rule that says carbon or anything in its group must make 4 bonds. So Si is making 4. And oxygen must make 2, and each oxygen is making 2. And then again, if we count up our dots, we have 2, 4, 6, 8, 10, 12, 14, 16, just like we had said. Okay. Now what's the shape of this molecule? We look at our center atom, right? Silicon. He is our center atom. Silicon only has 2 sides that have electrons. He does not have electrons on the top. He does not have electrons on the bottom. So that means we only have 2 domains. That means those atoms are going to be straight across. This is a linear shape. Bond angle of a line, 180 degrees. Okay. All right, now we got to take a look at the electronegativity differences. On your chart, the electronegativity for Si is 1.9. And the electronegativity for oxygen is 3.0. Okay, so if we subtract 3.0 minus 1.9, we get a difference of 1.1. That means that this bond between silicon and oxygen is a polar bond. Now we have to, if it is a polar bond, we have to draw the arrows. So let's do that. So let's draw our molecule here. And let's draw our arrows. Who's pulling harder? Well, it's whoever has the biggest electronegativity, which is oxygen in this case. So we're going to put our arrows towards oxygen on both sides. Now, to figure out if this entire molecule is polar or nonpolar, you have to look and see if they're pulling in equal and opposite directions. In this case, one oxygen is pulling to the left, the other oxygen is pulling to the right. They have equal strength. That means that it is equal and opposite. So this is a non-polar molecule, right? Because one oxygen is pulling in one direction, the other oxygen is pulling in the other direction. Nobody's winning the tug of war. So the electrons are going to be being shared fairly throughout the entire molecule. So it's nonpolar. So if it's nonpolar, it will not dissolve in water and we cannot smell it. because it cannot get through the water-based mucus in our nose to go hit the receptors in order to hit our brain. Okay. All right, let us do one more. And it's the last one because that's all I've really got room for. All right, HCF3. Okay, so first off, again, let's do our number of valence electrons. H has 1. Carbon has 4. Each F has 7. We have 3 F's, that's 21. 21 plus 4 is 25, plus 1 is 26. So in our Lewis dot structure, we'll have 26 dots. All right, so HCF3, who do we start with? We always start with the one that makes the most number of bonds. That's right, carbon. So let's put carbon in his 4 dots. We'll bring an H over with his dot, and we'll bring the F's over with their dots. All right, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 dots. We did it right. Nice. Okay. All right, structural formula time. Again, remember, it's the same thing. It's just lines instead of dots. All right. The shape of this molecule, well, we got to look at our center atom, right? Our carbon. Our carbon has 4 electron domains. All 4 sides have dots on them. And look, all 4 sides are bonded to an element. Okay, so if we have 4 sides and they're all bonded, that means it's going to be called a tetrahedral shape. And the bond angle of tetrahedral is 109.5. Again, you just have to memorize it. Okay, so for this one, unlike most of the previous ones, we have 3 different atoms making up the bonds of this molecule. So that means we have to do a couple of different electronegativity differences. So we have to look at each bond separate. So if we take a look at our first one, all right, which is, I don't know, let's just do carbon and hydrogen first, okay? So the bond difference between carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. That difference is 0.4. Is that polar or nonpolar? That's right, it's nonpolar. That means we don't draw an arrow, okay? So we don't need to draw arrows for carbon and hydrogen because they're nonpolar. Okay. All right, so next up is we've got carbon and fluorine, carbon and fluorine, carbon and fluorine. Okay, so let's do the difference between carbon and fluorine. Fluorine has an electronegativity of 4.0. Carbon has an electronegativity of 2.5. If we subtract it, we get a difference of 1.5. This is polar. Okay, remember versus nonpolar. If it's polar, we gotta do our arrows. Okay, so let's redraw our structural formula real quick. So we have C, H, F, F, F. Okay, and let's draw arrows. Okay, so for the top, who's pulling harder? Well, it's the one who has the highest electronegativity. Fluorine pulls harder, so we're going to put an arrow up to the fluorine. We're going to put an arrow over to this fluorine. We're going to put an arrow down to this fluorine. Do we put an arrow between C and H? No, remember, because it is a non-polar bond. So we don't put an arrow there, all right? So now what we have to do is we have to analyze our arrows. Do we have equal and opposite pulling in all directions? Well, let's take a look. We have an up arrow, right, which is canceled out by a down arrow. Okay, so these two guys cancel each other. We have a arrow pointing to the right, but do we have an arrow pointing to the left? No. We don't have equal and opposite when we're taking a look at left and right. So if we don't have equal and opposite, that means we have a polar molecule. This side will be slightly negative because it's going to be attracted to those electrons more on that side. This side of the molecule would be slightly positive. It's a polar molecule, which means yes, it will dissolve in water, and yes, we will be able to smell it. Okay? All right, so that is a tutorial about how to finish up the rest of this chart. Okay, I've done 3 with you. You have 3 to do on your own. Make sure that you follow all the steps. If you need to, you can go back and rewatch this video step by step, pause, rewind. Okay, just do your best, all right? But make sure you're actually trying. I don't want to come back to next class and be like, I don't get it. All right, I made this half-hour video so you guys can understand how to do it. Okay? All right, so good luck with this, and I will see you next class.